So welcome everyone to our regular Thursday seminar series. We're very pleased to have Lutz Warnke with us today, who's moving soon from the University of Cambridge to an assistant professorship at Georgia Tech, which, as many of you will know, has a very strong mathematics department. Particularly, there are people there I know in areas like harmonic analysis. And Lutz's interests, he'll tell us more about, of course, but they veer toward combinatorics and probability. And he's going to talk about the random D process, which, what I understand from the abstract, is that this is an interesting sequential way to generate D-regular random graphs that give some cool phase transitions, and about which he'll tell us more in a minute. So thank you very much.
So thank you very much for the elaborate introduction. Thanks for giving me the chance to speak here. So everything we'll talk about today is joint work in progress with Nick Wormald from Monash University. And really the topic lies somewhat at the intersection, say, of classical Erdös-Rényi random graphs and random D-regular graphs. So let me start by reminding you the way I want to look at the classical Erdös-Rényi random graph model here. So here I want to look at it in a sequential way. So the idea is we start off with an empty graph on n vertices, say these red dots. Then I want to step by step always add a new random edge to the graph. So maybe like this. And I should say, for the purpose of this talk, it doesn't matter exactly how we sample these edges. So you can sample the edges with replacement, without replacement, or in fact, instead of sampling a random edge, you can just sample two random vertices and pretend that they're the endpoints of your edge. It makes no difference whatsoever. So what are the typical questions we tend to ask about these processes? So in this talk, we're going to focus on the typical properties of these processes after we've inserted roughly a linear number of edges. Okay, and furthermore, I'm not really interested in what happens with the graph on 10, 20, or 30 vertices. I have no idea. What I'm really interested in is the properties of large random graphs. So formally, what we're going to look at is the case where the number of vertices n formally tends to infinity in the end. So how do we make this formal now that we talk about typical properties and so on and so forth? So as usual in the area, we're going to look at properties that hold with probability tending to 1 as the number of vertices tends to infinity. And typically such properties we're going to abbreviate with high probability, or WHP. Note that this really makes rigorous this idea that we're interested in large random graphs, because if you want that some property holds, say, with probability at least 1 minus epsilon, then this tells you, indeed, if you just make n sufficiently large, it will hold with that kind of probability. So what is now this phase transition phenomena that we're interested in? So this is the informal picture I like to keep in mind. So the idea is that, look, we start off with this empty graph. At the beginning, all the vertices are isolated, so all the components lie in components of size exactly 1. So now we start adding more and more edges to the graph. So maybe, a few larger components start emerging, but still everything is basically very small. We're still here in such a situation where all the components stay at most logarithmic in size. But then really in my opinion, really remarkable discovery of Paul Erdős and Untitled was that at some point, as you start adding more and more edges to the graph, at some point there's going to be some very special point, so that if you're in this situation and you just add some tiny amount of edges more, say epsilon n edges more to the graph, then the complete picture completely changes. Then one very, very big component emerges, and everything outside that component is again small. Okay, and we often call this actually the giant component in random graph theory, because it is truly a very, very big or giant component that contains a constant fraction of all vertices of the graph. So it's really, really big. And so some people also claim that maybe you can motivate this kind of behavior from the applications perspective. It's not really my area of specialty, but for example, if you think about the spread of the diseases in such components and so on, then on the left-hand side, if one person gets infected, you just have some local outburst, whereas here on the right-hand side, if you infect someone here, well, it's not a very good situation. Okay, so this is the intuitive picture I like to keep in mind, but of course we need to be a little bit more formal. What do we mean here? And this is perhaps the most basic way to state the classical result of Erdős-Rényi, which says that, intuitive words, that this phase transition phenomena that actually happens after inserting roughly n half many steps. And so one way to make this formal is, okay, let's look at some fixed t smaller than 1/2. And then the largest component after t times n many steps is with high probability, meaning with probability tending to 1 as the number of vertices tends to infinity, at most logarithmic in size. And intuitively, we're here on the left-hand side. Whereas if we look at some fixed t larger than 1/2, then with high probability, the largest component is concentrated around some deterministic function, which is of linear order. And the second largest is much, much smaller, say at most logarithmic n. We're in this situation here. Okay? So this is sort of maybe one way to formalize the basic Erdös-Rényi phase transition, where you go from logarithmic size largest component to linear size largest component around n-half many steps. Of course, nowadays we know much, much finer details about the phase transition. We know very precisely what's, say, the distribution of the size of the largest component, what happens if t is not just smaller than 1/2 and bigger than 1/2, but if we actually let t tend to 1/2 as a function of n, then we know very, very precise results. But that's not the direction I want to go today. So today I do not want to prove finer results about Erdös-Rényi. Rather, what I want to do is I want to look at more complicated models, more complicated random graph models, and prove a similar kind of result. And for this, I often like to go back to some very early papers of Erdös-Rényi, which I think are not as well known as they should be. So already in a paper in 1961, actually, they actively encouraged the study of more complicated models. In particular, I like this quote here, where they say that basically, of course, Erdös-Rényi is not useful as a realistic model. We need to study more complicated models, and I think this kind of argument was put forward quite prominently some 20 years ago by a lot of people, seemingly unaware of this very early reference. And in particular, one model that they suggested, and I think they were motivated by some applications or some ideas from chemistry, maybe where some element or something can only interact with a bounded number of other elements. So they suggested the following. Okay, let's put down the edges one by one. Now the probability that a certain edge is inserted in the next step, that should be somehow a function of the degrees of these vertices. Okay, so if a vertex has a certain degree, this should affect the probability that we insert the next edge there. And the model that I want to discuss today is in some sense a very special case of this. It's a model where we actively want to prevent the creation of vertices that are larger than d. Okay, so whenever basically such a vertex here already has degree d, then this probability will simply be 0. And this is the so-called random d process. So where again the basic idea is we just put down these edges one by one, but we just make sure that we never create a vertex of degree larger than d. Or more formally, as Erdös-Rényi, we start off with this empty graph and then vertices. Each time we sample a new random edge, but subject to the constraint that this does not create a vertex of degree larger than d. Or if you want to think it more algorithmically, you can also say, okay, you look at all the edges of the entire graph, we check which edge would I be allowed to add in the next step without creating a vertex of degree larger than d. I put all these valid edges into a bag, and I just grab one of them at random. So let's maybe do a small example to get some feeling how such a process might look like. And let's focus for simplicity just on the case, say, d equals to 3 for the moment. Okay. The first thing that we notice is that actually there are two different kinds of vertices in this process. So there's what I call active vertices and inactive vertices. So the main point is that in the d process, you can never create a vertex of degree larger than d. So somehow these vertices, which currently already have degree d, they should have a special role. And their special role is that they don't play, they're sort of useless somehow for the evolution of the process, because we can never attach anything to them. Okay, so somehow we should focus on the active vertices. So now we can, of course, do this small example. Maybe I think now we're going to create maybe here an inactive vertex, and so on and so forth. And I should mention again that for most of the properties that we study today, it doesn't matter if you sample here a random edge subject to this constraint, or you do something slightly different. So suppose we're cheating a little bit and we just each time sample two random active vertices and connect them by an edge. Okay, so for the sake of analysis, it makes almost no difference. The only time where this can create a problem is if you have two active vertices which currently are already connected by an edge. Okay, but one can show that this happens very rarely and transfer all the results between these two models. Okay, so this is the random D process. Let me maybe make a few more remarks here. So clearly, this model contains, this is a special case, the classical Erdös-Rényi random graph model. Just take d equals to n or n minus 1, and simply the degree constraint has no role whatsoever. And I want to emphasize that, that this model really differs from what some of you might know as the configuration model, and I might say a few more words about that in a moment. So in particular, it seems that this model gives might give a different distribution than uniform deregular graphs. And of course, there's nothing which says that every vertex should have degree at most d. In principle, you can also study some much more general case where you say, okay, vertex vi can have maximum degree di, then we can study also the evolution of these processes, or you can also look at hypergraph variance. So instead of each edge having 2 vertices, each edge can have in general k vertices, and you can also study such variance. But let me, for the purpose of this talk, just stick with the case where every vertex has this degree d constraint. Okay, so what about now some further motivation? So besides this sort of very earlier paper by Erdös-Rényi, I think this model in particular is an extremely natural model for trying to generate deregular graphs. So I'm pretty sure that if you give, say, your undergraduate students as a task to try to generate deregular graphs, a lot of them, I think, would try to use this kind of greedy model. I think coming up with this sort of, for example, configuration model, which is sort of specifically tailored for trying to generate uniform graphs or close to uniform graphs, it's somewhat maybe not the first thing you would try.
Sorry, I thought deregular meant all degrees were d, but some of these degrees are less than d.
Oh no, so the point is you want to look at the graph, say, at the end. Okay, so...
We just keep going into this.
Yes. Right, so in the configuration model, you also sort of, if you think about it in this algorithmic way, you also gradually add one edge after another. So I think in that sense, it's a very natural greedy model, and you can apply a similar paradigm also to a lot of other situations. If you just want to avoid, for example, it's a very famous process, the so-called triangle-free process, which was analyzed by Tom Bowman and others, where you say each step, I want to greedily avoid creating a triangle. So in each step, you just sample a random edge subject to the constraint of not creating a triangle. And in principle, you can do this with any monotone property. So this is a very robust paradigm for generating interesting random graph models. And one thing I like about this model in particular is that it again emphasizes the time evolution aspect. I think this is something that's often somehow ignored or neglected, the fact that we are nowadays studying a lot of networks that evolve over time. So something like a Facebook or road network, they're not static, but they evolve over time. And the question is, does such a time evolution also have sort of impact on the properties that we can observe? Okay, so you might say, for example, maybe for simplicity, a road network, maybe that's, so suppose it would really be somewhat planar, and some people might suggest, okay, we should study random planar graphs as a sort of a toy model for understanding these things. But then the question is, but now you've completely ignored the fact that clearly these streets, they evolve over time. You just don't generate all these streets in one go, but they really incrementally are generated over time, and this might really have some impact on the properties of these networks. The second motivation, which maybe is more of a technical nature here, so it turns out that surprisingly, the question whether this process has a phase transition or not, this was open for quite a while. So there's, for example, this very influential survey by Nick Wormold, where he, in the context of probabilistic combinatorics, was promoting the usage of the so-called differential equation method, which allows you to understand such random processes. And perhaps the most recent success from that survey, the most open problem that was solved recently, was this so-called triangle removal process, which some of you might have heard of. This was a breakthrough by A.L. Lubetsky, Tom Bowman, and Alan Fries. And I think besides that, this phase transition in this random D process is one of the last open problems from that survey. And maybe as a final point, this is something that I care about a lot, is that this process can be used as a very convenient testbed for developing some tools and techniques in the context of the phase transition. So the main point is now that we're extremely good at analyzing, for example, the Erdös-Rényi random graph process, the configuration model, et cetera, And the main point is that we can analyze these models so extremely well because there's a lot of independence present. Okay, we can sort of generate these models in some way as a sequence of independent random choices in a nice way. And then we can get these very strong results. But in such processes as here, where really the time evolution plays a role, for example, as we've seen, this set of active vertices changes in this very weird way, it's very hard to use these classical methods that work for Erdös-Rényi or the configuration model. So this is really a convenient test bed for trying to push the methods in the area. Okay. Yes?
Can you say more precisely what this open problem is?
The open problem is there a point, a critical point, where the phase transition happens? So in Erdös-Rényi would be Tc equal to 1/2.
So T is fixed, is it?
Yes.
So T could be 1 billion, and
Yes.
still don't know, frankly.
It was open prior to our work, yes. So the question is whether it's a deterministic time. So to show that there's a giant at some point is not so difficult. But you need to show that it's sort of a deterministic time. Yeah, I mean, of course it exists, but you need to prove it then. Okay, so let me say a few more words about what properties are sort of known about the D process. So I think this we already discussed briefly earlier. So the question is, what properties does the graph have at the end, for example? And this was a paper by Ruczynski and Wormald where they show that the final graph is with high probability deregular. Okay, so indeed it generates nice deregular graphs. So this was answering actually a question of Erdős from 1985. Perhaps for this talk, the most interesting thing is that there are some differences that you can observe for the case d equals to 2. Okay, so Ruczynski and Wormald, they calculated, for example, what is the expected number of triangles at the end when you have this d equals to 2 case here. And what they were able to show is that the expected number of triangles actually differs from what you would see in the uniform model. A similar thing happens if you look at the probability of being Hamiltonian. So this is a very long, complicated paper by Telks, Wormald, and Zhu, I believe. So I think it was already announced in 1993, actually, but it took a few years to write down. So what they were able to show is that the probability of being Hamiltonian is something like constant over square root n. And again, they were able to show that the constant slightly differs from what you see in the uniform model. Okay? So again, we see some differences. Okay, so now let's return to the question of the phase transition. So the question is, can we prove that there's a deterministic time at which the phase transition happens, at which the largest component goes from logarithmic size, say, to linear size? Okay, now we can take as a first step, let's just do the following for simplicity. Let's just do the following thought experiment. Let's suppose we just stop the process after a certain number of steps. Okay, so after t times n many steps of the process, we have a certain number of degrees that have currently still degree 0, certain number of vertices of degree 1, and so on and so forth. And now we can use this sort of very widely used heuristic, and somehow only the degrees should matter. This is some paradigm that's used all over the place. Let's measure the degree sequence and ask when does this graph with this degree sequence have a giant component or not. Okay, so in other words, we can sort of observe here the degree sequence after t times n many steps, and then ask when does a uniform random graph with this degree sequence have a giant component. There are certain criteria for this. Some people call it the Molloy-Reed criterion, or you can think of it as a natural criterion. When does a certain branching process become supercritical? And we can apply that here. And what you will observe is that if you use just the degrees to predict the phase transition, then you get the wrong answer. Okay? So if you look at this in the D process, say for D equals to 3, then say simulations would suggest that this phase transition after say 0.5772, but this degree heuristic would tell you something different. Actually, it would tell you that the phase transition happens later. Okay, and I think this is sort of a nice example which shows that indeed we need to be very careful about such heuristics if the time evolution can really make a difference.
So I know you're good at simulation, but how do you do simulations to get correct with 6 figures?
Okay, so
one differs only in the last figure.
Okay, so this is actually I generated this. These are actually in some sense rigorous results because I have a way to rigorously calculate this in the D process using our result, and I also have a way to do this rigorously because the number of
the degree
because they follow a differential equation. So you can plug exactly the solution of the differential equation into the Molloy-Reed criterion and then ask, for example, Mathematica to say, okay, I want to have this up to 20 digits precisely, and then you get these results. So yeah, so these are actually not based on simulations, but they're actually rigorous results. But yeah, the interesting thing actually happens for d equals to 2, but we'll come to that later. There the simulations are, yeah. Okay, so the main point I want to make here is that indeed something more delicate seems to be going on. So let's maybe first do a simplification. So as already mentioned, there's of course a difference between how big d can get. And so again, using simulations or rigorous results, you see that this is the kind of, the point of the phase transition very, very quickly goes to 1/2. This is what it's very evident, not only in, say, these simulations of these differential equations, but also in simulations. It's very clear that it very quickly goes to 1/2. And we can also understand why that's happening, actually. Okay, so the first claim I want to make here is that in some sense finite d is really the interesting case. If d gets large, then we know what's happening. And so the idea is the following. Recall that we are, on the one hand, we have this Erdös-Rényi random graph process, which just puts down edges one by one, always in a random fashion. But then we have this d process, which you can think of in a similar way, but it somehow rejects all edges which create a vertex of degree larger than d. Okay. Furthermore, in the Erdös-Rényi random graph process, it's not so difficult to see that if you look at the Erdös-Rényi random graph process, say after a linear number of edges, then the proportion of vertices which have degree larger than d, that drops exponentially in d. Okay, so in other words, if you just make d large enough, then there's going to be, say, just epsilon n many vertices which have to be larger than d. Okay, so this sort of suggests that now we put in one process down the edges just purely at random, and we just create some epsilon n many vertices of degree larger than d. This suggests that this should be very similar to this behavior of the d process, where you just put down random edges which never create a vertex of degree larger than d. Okay, and there are ways to make the connection between the two rigorous, but I think this already provides some evidence for the fact that if d is just very large, the phase transition and the d process and the Erdös-Rényi process will happen at a very similar point in time. Okay. So in fact, this heuristic is very strong in the sense that if you just not look at fixed d and then let d tend to infinity, but rather you let d tend to infinity as a function of n, then this kind of comparison, what you can squeeze out is that actually the critical point is exactly equal to 1/2. Okay, so really, in our further analysis, if you want to understand the d process, we can restrict ourselves to finite d. And this table also suggests that probably the most interesting behavior happens here at d equals to 3, not say at d equals to 10 million. Okay, so what is maybe the first result that I want to mention here is, so the first result is that for fixed d, we can exactly prove the existence of the phase transition exactly in this classical basic Erdös-Rényi result. Okay, so for any d at least 3, there's a critical time at which the phase transition happens in the sense that you go from logarithmic size to linear size. Okay, so if t is bigger than tc, then we even get this concentration around some deterministic function of linear size, and we can also prove that the second largest component is of logarithmic size. In fact, something much stronger is true. You can even prove that outside of the largest component, you get some exponential tail, but maybe that's just for the fans of random graphs. So in particular, this solves this problem of Wormald regarding the existence of the phase transition. For that, actually, something much bigger would be enough, right? It would just be enough to show that if t is smaller than tc, then this is still sublinear. But we can get these very strong results. Furthermore, I want to emphasize that the way I formulated the result is almost exactly the same as I formulated for Erdös-Rényi. So if you insert here, replace this tc of d by the 1/2, then you would basically get exactly the same statement as in Erdös-Rényi here, up to these specific constants. So you might wonder now, well, what is the most difficult of all these statements to prove here on the slide? And perhaps surprisingly, the most difficult statement here is to prove something like this, that the second largest component is of logarithmic size. This turns out to be in the d process quite delicate business. So it turns out that in Erdös-Rényi there's some shortcuts how you can do that. So there some tricks how to very quickly show that the second large component is logarithmic size. But these tricks, they're very specific to Erdös-Rényi. They're not very robust, so if you try to apply them to more complicated situations, they very quickly break down. So a lot of work goes into showing this kind of result here. So now we've understood d tending to infinity, d at least 3. So what about now the remaining cases? Well, of course, d equals to 1 is pretty boring. We're just adding and matching. There's nothing really to say about that. So now what about the case d equals to 2? And it turns out that there the behavior is a little different. And in some sense, what happens is that the giant in some sense only appears very close to the end. And this causes some headaches or some differences. So what I mean by in the end is, recall if we're looking at a 2 process, so every vertex can have a degree at most 2, then at the end we should have like basically n, we basically make n steps in the process. Okay, by the result of Wormald-Rutchinski, we know that the final graph is 2 regular, so we really end with n after n steps. And we can prove that if t is smaller than 1, then again after t times n many steps, the largest component is still of logarithmic size. Okay, so basically almost all the way to the end, all the components are still tiny. But then a lot of action happens at the end. A lot of action happens at the end. And in contrast to the previous case, we get non-concentration of the largest component. Okay, so if you look at what's the probability that the largest component has at least constant times n vertices, this is asymptotic to some function f of c, which is strictly between 0 and 1. Okay, so this really shows that we do not have this concentration behavior that we usually observe in for example, Erdös-Rényi, but we actually get here non-concentration behavior, which more resembles what you would, for example, get in the for random 2 regular graphs. Okay, and this particular was actually mentioned as an open problem in this Quo Vadis graph theory conference from Alaska from 1990 by Balinska and Quintas. I think this is some.
I guess it's, if you want to use the board.
Yes, okay, I'll just write here for a second. So in particular, their question what happens for c equals to 1/2. And so I should say that the function here is quite complicated if c is very small, but for c so 1/2 or c bigger than 1/2, there's a nice formula. So for example, the probability that the largest component is at least n/2 is, I think, asymptotic to something like the logarithm of square root 2 plus 1. I would need to check, but it's something that you can write down, and it's surprisingly nice formula.
This is for your 2 process.
Yes, yes. Okay, so I think this is what you're referring to. That it turns out that in this 2 process, this function f is exactly the same function that you would also get in the configuration model. Okay, so if you study the standard configuration model, where you set all the degrees d equals to 2, then you would get exactly the same function. Okay. So this is sort of in contrast to the previous results on the 2 process, where we looked at, for example, not we, but Rutchinski and Wormald looked at the expected number of triangles, for example, where they observed that the expected numbers are different, or they looked at what's the probability that you have a Hamiltonian cycle. There's some things that are different. This is one case where you get the same function also as in the 2 regular case.
Will you also, if you look at smaller cycles, I mean, at the end, we will just have a union of disjoint cycles, except possibly one if you have an odd number. So, but will you get also if you look at the small cycle, let's say cycles of length 3 or 4, so same asymptotics as for the uniform regular 2 regular graph, or is it just for the big ones?
Okay, so the situation is quite complicated. So I think so for the small cycles, I think they checked for the case for 3 for the triangle, and there the number is different, and the conjecture basically is the following, that as the cycle length tends to infinity, then the expectations in the 2 models should be similar. So we tried a little bit to prove it, but it's not so easy. Maybe
Did you succeed proof for L2? The second largest one.
Okay, so the proof extends here to any finite number. So if you, for example, look at L1 up to Lk, you get a similar statement with constant c replaced by ci.
And then I show you got the joint distribution also.
Yes. So, but the proof technique we use here is, if you look at very small cycle lengths, then our proof technique is not good enough. So I think we can only do up to m to the 1 minus delta for technical reasons. Yeah. So the conjecture is that actually the final graph of this is contiguous to a two-regular graph. But proving that is quite a delicate business.
That's a pretty great conjecture, though.
Yeah, so this is not, okay. So in general, I think it's for the D, I think Nick put this in some survey many years ago, that in general for any D it should be contiguous, but I think, after we proved this, I think there was some hope that maybe one can push it through, but it's not so easy. Problem is it's not so easy to write down what's the probability that a certain graph appears in this process. For example, what is the most likely graph? Is it the Hamiltonian cycle or not? Right, anyway, so. Yes, but
Right, but that, the contiguous version of the conjecture, everything we've talked about so far fits nicely into that.
yes.
Started with that.
But yeah, how to prove it is.
Just so I know, you guys are talking about, what does contiguous mean?
Okay, so it means that if you have some property that holds, say, with probability 1 in the uniform to regular model, then it should also hold with probability 1 at the end of the 2 process.
You mean
And vice
probability
versa.
tending to 1 as n goes to
Yes.
infinity?
Oh, yeah. I don't know what they. Yes.
No, but I mean this is important because point of a contiguity. I mean this is something that took me a long time to learn, so that's why I try to be careful with it. But some statisticians here ought to know it by heart.
Okay.
Because this is a concept from statistics. The term comes from statistics. So that's why I guess many people know it. But it really is asymptotic when you look at n go to infinity, increasing sample sizes. So that said, if you have something asymptotically only with probability to go to 1, precisely. Lutz said in one model it should do so in the other model.
Do you
But
have some class of properties? I mean, is all properties? Or?
no, I mean you
fix
can't
one
take
A
you
and
look
Z.
at it. This should hold for all properties.
Any
Say that the
property,
models, yes, it say that the models are contiguous. It really means any property.
So-
So it is a.
It's
so what I-
almost the same distribution, it's just not quite.
Well,
Yes,
It's as
because-
close as you can get.
But-
Yes, because what can happen is that if you have something which holds with some probability which does not tend to 0, and tends to probability tends to half in one model, it may convert to some other limit in the other. So the way I think of it is that this is kind of finite or asymptotic version of having 2 probability measures which are mutually absolutely continuous, but not necessarily identical. One can actually formalize that.
That's how Bickel in fact defines it in his.
Okay, good. Yes, I remember when I introduced this in context of random regular graph, was David Aldous that told me that this concept was called contiguity. It was a well-known thing. So I'm grateful to David Aldous for reminding me about this.
Yeah. So
I think it goes much. I mean, this goes back a long time in history of statistics. I think.
I believe
I
that's
think
right.
this is even older than Bickel.
Oh, absolutely, Kolmogorov. It was in Kolmogorov. But Bickel used it very strongly in his semi-parametric work.
Okay.
I think Russus and Lacan.
Yeah, okay, Lacan.
yeah. So I always think of it though from the random graphs perspective. In some sense, it's a very weak property, and so it's just enough for what.
It's very strong.
No, I
because
think
you
no,
look
I
at
don't.
all properties.
I don't agree. I don't agree. I think it's a very weak property because it only tells you something about properties that hold with probability tending to 1. It doesn't tell you about anything else. In the other case, it just says that these probabilities they're sort of almost a constant, so they can be distorted by a constant at most. But it doesn't really tell you anything about properties that do not hold with probability tending to 1. I think it's a very weak property.
I don't agree. I think it's a very strong property. As I said, it says asymptotically it says that you have
But it-
absolutely continuous.
But it doesn't tell you
measures.
anything about, for example, if n is not very large.
No, of course, it's an asymptotic property. That is, but I mean, anything you said here so far have been asymptotic results when n go to infinity. So they don't say anything when n is not large.
No, that's not true. So these are not these subsequence-based proof results. So they really tell you something. In principle, I can tell you always about there's some finite n and then the proof works. So some of these results even hold with like probability 1 minus n to the minus 99 or something. So it should tell you something even about small n.
Are you going to talk at some point about the speed of convergence?
No,
I mean, I asked just because, you know, there are some limit theorems like the array logarithm, which are beautiful, but, you know, it sort of takes forever for the asymptotics to set in, and central limit theorem is useful because it's amazing how quickly it does. So do you have any sense at all about how quickly things might set in? You've done simulations.
Yeah, I mean, I think I only simulated this for small n, so like 10 to the 8 or something. But then you clearly already see the effect, so it's very quick. I mean, for Erdös-Rényi, I think if you simulate, you already see something with 1,000 vertices, right? And it's very amazing. To be honest, I didn't even try simulating this with a few thousand, but I would not be surprised. I guess like if you do 10,000 or something, you already see all the effects. Okay, so now, so we can discuss. Oh yeah.
It just, I mean, you mentioned at the beginning that you can interpret this as this series of results as being about graphs that are star-free for some size of star, and you mentioned about graphs that are triangle-free. Are there other examples that are as natural as triangles and stars, or I mean, just conceptually, does it feel like there should be something else for which similar approaches would work, or is it sort of not clear beyond that what the next step would be?
Okay, so
I'm not thinking
in the
so
context
much
of
about
forbidding
the
subgraphs,
but yeah.
for example, I think this, as you rightly say, that you can think of the D process forbidding a certain star. I think that's probably the most interesting case, because if you think about, for example, triangles or any denser graphs like larger cliques, they appear much later in the uniform random graph model. So you only have like a constant number of edges. So you need something that, like stars, for example, they appear earlier. At sublinear size, you need to look at something like that.
So it's about the ratio of nodes to edges or whatever.
The maximum density, yeah.
Got it.
But I think, you know, it's more. I think a lot of people now say that this is sort of first instance of this triangle-free process paradigm and so on. But I think the motivation here really comes from the fact that you get these deregular graphs out of it. I think this was really the clear,
the other way around.
clear motivation. There's another model though, which one can look at, which you're mentioning, where you, instead of always adding a random edge, you always select a random vertex, which is currently has to be less than D, and then you attach with a suitable number of neighbors in one go to fill up the maximum degree. This has also been studied. This is the thing called star process, which probably is also a very natural variant to look at. Okay, so so.
But this feels, well, this is nicer because you can more obviously recover Erdös-Rényi by letting D equal n. I'm not sure if the other one can do it as nicely.
I mean, it's just a nice feature that you can recover Erdös-Rényi. I would not consider it an essential part of the theory here, especially because if D tends to infinity, basically.
But that turned out to be important with what you showed later, because it sounds like it doesn't matter how slowly D approaches infinity, the same effects take over, which is that in the end it doesn't matter.
Okay, so I'm supposed to speak until 12 or 10 to 12? Or?
Oh, I guess, how many more slides do you have? I mean, until 12 is fine.
Okay. I'll try to be a little quicker then. Okay.
No. I mean, it's a small group, so I think if people have to leave at 12.
Yes. Okay. So I realize that we have a very wide range of expertise in the audience today. So I'll try to just say a few words about the proof philosophy, not so much about the technical details here. In particular, I want to again advertise this one parameter, which I think, you know, if you just want to memorize one thing from the talk, then maybe just memorize this parameter, which I think is very powerful in this context. So it's a so-called susceptibility, which is a concept from mathematical physics, really. And the way I like to think about it is the following. Suppose I give you some graph, And let's just sample a random vertex from that graph and ask, what is the number of vertices in the component containing the vertex I just selected at random? Okay, so select a random vertex, what's the number of vertices in the component containing that vertex? And the susceptibility is exactly the answer to that question. Just to be sure, so what's the probability that we select one particular vertex from the graph if it has n vertices? That's probability 1 over n. And then the C of B, that's the number of vertices in that component. Okay? And this gives you some kind of measure for the component size distribution. Okay, let's try to first get some feeling for it. And for that, it turns out it's very useful to rewrite this in a very simple way. So suppose your graph has the components C1, C2, etc., etc. Then it turns out that you can write the susceptibility as 1 over n times all these component sizes squared. Okay, and this is a basic rewriting argument. Just here, for example, this component consists of Cj vertices. So you can just rewrite this sum like this. Okay, so let me not say too much about it, maybe. Simple double counting argument. Okay. So once we have this representation, now we can start playing around with it, getting some very basic idea what's going on. And so I'm going to do something that looks completely crazy. So I'm going to say, forget about all the components for the moment. Just let's look at the largest one. Just look at the largest one, okay? So in particular, if we have this sum of squares representation, then the susceptibility is at least the largest component squared divided by n. Okay. So now from this we can generate these two inequalities. And this already gives us some idea what might be going on. So recall our goal was to study when is there a linear sized giant component. Well, if there's a linear sized giant component, then this inequality tells us that the susceptibility is at least linear in n. So in particular, if the number of vertices tends to infinity, the susceptibility should diverge. Okay, so linear sized giant component implies diverging susceptibility. But what about the other way around? Of course, now if we know that the susceptibility is bounded, we plug it again in the same inequality here, then we see that the largest component is still of size of most square root n. So it's definitely sublinear. Okay, so now we have these two nice things. Linear size giant component, diverging susceptibility, finite susceptibility, sublinear size, largest component. So maybe the point where the susceptibility diverges, maybe that coincides with the point where the giant component appears. And I admit at this point this looks like a very, very weak heuristic and very, very optimistic, but there's some good reasons to believe that this is true. So in particular, a similar kind of heuristic is widely used in percolation theory on infinite lattices, where there are probably two different ways to define a critical point. One is to say, let's look at the point where there's the probability of having infinite sized giant component as positive probability versus the point where the expected size of the cluster containing the region where that diverges.
Sorry, I'm not sure which term you're trying to prove. Is this the one for t greater than 3?
Yes. Yes, yeah. And so actually, I'm not going to really prove anything in this talk today. I'm just going to talk something about these parameters. And yeah. Okay, so this is sort of the hope is that maybe this blow-up point of the susceptibility is the right quantity to look at. There's some motivation from classical percolation theory, and it's also true for Erdös-Rényi random graph processes. Okay, and I just want to do a very quick convince you that indeed sort of at time t equals to 1/2 or after n half many steps it blows up in the Erdös-Rényi. Let's just check that. Okay, and here's for example one very nice way to look at this. So recall I said we have this representation of susceptibility as this sum of component sizes squared representation. Okay. So now let's suppose for the moment that we have these two components here of size A and B, and we join them together by an edge. How would that now affect, say, the susceptibility? Well, if we add this edge to the graph, we create a new component of size A plus B squared. So we get some extra contribution here, but we need to subtract off the old contribution. This was this A squared and B squared from the old components, but these are now destroyed. Okay, so the nice thing is now that there's some factoring happening here. So we just have a 2AB left. And this 1 of n was just here because we had this 1/n normalization here, any susceptibility. Okay, so if we add such an edge, we know that the susceptibility changes by 2ab over n. Okay, but what do we do in Erdös-Rényi? In Erdös-Rényi, I said we just add each time a random edge to the graph. Or in fact, I said, forget about the random edge, let's just pretend that we're sampling 2 random vertices. Okay? So if we look at now the expected change of the susceptibility, what happens if we sample two random vertices? We need to the 2 endpoints of the edge, right? Each of these endpoints now corresponds to a purely random vertex. So the size that we were expecting to hit, or the expected size of that component, that's exactly the susceptibility, right? We're sampling a random vertex from the graph. What is the expected size? And so on average, we should replace this guy here by 2/n times the susceptibility squared. Okay, there's some slight cheating here because in principle it could happen that you hit the same component twice. Let's just ignore that here for the moment. Okay, so once you have that, then it's sort of there's some nowadays standard machinery available which tells you, okay, if your random variable satisfies on average such an equation, and you say make this guess that the susceptibility should scale like some deterministic function of t, then this function s should satisfy this differential equation here, s prime equals to 2s squared. So this is an approach that's used very widely, say, in mathematical physics, where one can argue that this corresponds to some self-consistency condition. Okay, so if this is true, then by looking at these expected one-step changes, you can see that then the function must need to satisfy this differential equation. But nowadays, there's sort of mathematical techniques. So for example, the differential equation method of Wormald, or these early results by Kurtz, using martingale techniques, which allow you to convert that into rigorous results. You can say, yes, indeed, this quantity here should be tracked by this deterministic function with high probability. Okay, but if you solve this differential equation, the nice thing, Erdös-Rényi has a unique solution. It's just this 1 minus 2t inverse. So we see that exactly this thing blows up at t equal to 1/2. Okay, and we know that after n half many steps, a giant component appears in Erdös-Rényi, so this is all consistent with that. Okay, and so one thing that we can show is that a similar phenomenon also happens in the D process. But in some sense, I'm slightly cheating here in the sense that it's more of a consequence of our proof rather than that we use this in the proof. And so one of the reasons is that somehow the susceptibility is not really the correct quantity to look at, for example, in the D process. And one of the reasons is that somehow there was this effect that only active vertices played a role in the evolution of the process. Okay, so somehow all these vertices that are inactive, all the vertices that already have degree D, they should not really play a role anymore in the evolution of the process. And so, guided by the susceptibility, say, one can maybe cook up the following variant of the susceptibility. So which I would here call, for the purpose of this talk, say active susceptibility. So the idea is that we only want to focus on the active vertices. And so we want to sample a random active vertex, and then ask, so how many active vertices does the component of that randomly chosen vertex, randomly chosen active vertex contain? How many active vertices are we going to see there on average? And it turns out that this variant of the susceptibility would be the answer to that question. Okay? So what this says is, sample a random active vertex from your graph. How many active vertices, on average, will the component containing that vertex contain? Okay? Okay, so instead of sampling just a random vertex from the entire graph, we just sample a random active vertex. Okay? Now there's some problem which happens in some sense. So as I indicated, for example, the last slide for Erdös-Rényi, you end up with one nice clean differential equation. And it turns, for example, Spencer and Wormald did similar things also in other random graph processes. There you again end up with one differential equation for this susceptibility. But in the context here of this D process, we were not able to find one differential equation for this random variable. Okay? But what we could find is we could find order d squared many variables, which allow you to recover this this variable here. Okay, so it's like strengthening the induction hypothesis. We track a bunch of more information, and from that, all that information together, we can then recover this random variable. So one of the things that...
So where is the big of d squared? If you take equal to 3 here, how many do you actually need in that case? Do you remember?
Probably 9 or something like that. So the order d squared is only if each vertex has the same maximum degree. So if you, for example, allow different maximum degrees, so say suppose you have vertices of degree 1, 2, and so on, then it goes up to d to the 4 variables. So okay, but the main point I want to make here is just that, you know, we want to show something about the blow-up point of these differential equations, right? And so as soon as the number gets very large, it's not so pleasant to work with them, or at least for me it's not so easy to work with them. One difficulty here is that some of the variables that you want to look at, they're not monotone. Showing that variables that are not always monotone blow up is a bit delicate issue. So what we decided to do is we decided to come up with a different way to avoid this issue, right? Because I'm sure if you sit down for a month and analyze these differential equations, I'm sure you can do it. I'm sure you can prove that they blow up, but then I show you a different process, and then you again need to work a month. So I think it was time to try something different. And what we're sort of doing is we're trying to turn this paradigm of the differential equation method on its head. Because usually we say, let's try to understand the random properties of the random process using the differential equations, right? This is what we usually try to do. Predict properties of the random process using differential equations. But now we want to do it exactly the other way around. Now what we say is let's try to understand properties of the differential equation using the random process as a tool. And the way why this works is that we can take this sort of limiting perspective that's usually used often, for example, in the context of convergent random graph sequences and so on, or say even in the context of Erdös-Rényi, where you might say, let's look at the neighborhoods, for example, of a vertex, the iterated neighborhoods. Then Erdös-Rényi, we would say in a certain range, at least, that the iterated neighborhoods, say, for example, look like a Galton-Watson branching process in the limit. Okay, sort of, you can think of the neighborhoods, they look in the limit like a Galton-Watson process. And you can take a similar approach here. You can say, okay, after suitable rescaling, the process in some sense converges to these differential equations. Okay, after suitable rescaling, the limit is somehow are these differential equations. So now if you know that the differential equations have a unique solution, if you know that these differential equations have a unique solution, you can also go the other way around. You can also transfer properties from the process to the differential equations. Because if your differential equations would have certain properties that are not reflected by the differential equations, then because in the limit the process satisfies the differential equations, these other properties would allow you to find a second set of solutions to the differential equations, which is not possible in the context of uniqueness. Okay, so what I'm trying to say is, if you know that that the process tracks the differential equations, the equations have unique solutions, you can go in both directions. You can not only use the differential equations to understand the process, but also the process to understand the differential equations. And sometimes this is useful. For example, just to give you one idea what you can do, is you can somehow, in this context, for example, try to use random graph methods to prove some very, very weak statements about the evolution of the D process. Suppose I could say something about some tiny interval. Suppose I can say something about if we do epsilon n extra steps, can we then say something still about the D process? And this is what we managed to do using some technical arguments. But the main point is, if you can get some kind of rough control, then there's a way that allows you to translate that into an almost automatic proof that these differential equations must have a blow-up point. So what I mean is the following. If you have a certain rough control of the process, then there's a very careful way to write down the proof, where in the end it drops out automatically that that susceptibility must blow up at a certain point in time. There's no need actually to even analyze the differential equations. So this uses some ideas that we developed together with Oliver Jordan in the context of the analysis of Archaeopteryx processes, where we're exactly trying to avoid using differential equations. Because there we somehow ended up with an infinite system of differential equations, and we didn't know if it has a unique solution, so we needed to avoid using differential equations. But now it turns out that the ideas that we developed there can now also be used in the context of situations where we actually do have differential equations. It can be used to basically sidestep the analysis. Okay, so this is sort of what I really wanted to only say about the proof from a conceptual point of view. I really want to highlight the fact that there's this very nice random variable, which seems to be a very important parameter in a wide range of contexts, not only sort of in percolation on lattices, but also in these other random graph processes or the D process. In particular here, the susceptibility maybe was not quite the right variable to look at, but it sort of clearly guided us towards finding the right variables. First the active susceptibility, and then these order D squared auxiliary random variables. So I expect this also to be useful in other contexts. So let me then briefly maybe summarize. So we're looking at the phase transition in this random D process, and we observed these sort of two qualitatively quite different behaviors. So in these at least three, we observed more this Erdös-Rényi-like type behavior where we go nicely from logarithmic size to linear size. And for D equals to 2, we observed some very different behavior. We observed that there was some non-concentration of the largest component exactly at the end. Now I'll stop here. Thank you very much.
Thank you. Any more questions for Lutz? We're just about at the top of the hour, but questions if anybody has.
Well, yes, I've said a lot, but now it's maybe not be surprised given our current joint work here. I wonder, have you looked at the width of the phase transition?
Yeah, okay. So I expect it to be similar, exactly the same as in Erdös-Rényi. Yeah, so I started thinking about this with Thomas Rutschak the other week actually, but it's...
Sorry, I didn't understand the question. What's the question?
Okay,
Didn't hear what you said. What phase
so the question is now you want to look at, for example, this Tc plus minus epsilon. Now you want to let epsilon be a function of n. So the thing should be, for the experts in the room, it should again be this kind of epsilon to the 3n should be the right width of the window, but proving it is a little bit delicate.
What's TC? Do you know anything about the value of TC?
Okay, so depending on how you look at it, TC is either implicit or not, is explicit or not, sorry. So I can show that it's the blow point of a certain system of differential equations. So in that sense, it's nice. And I can also give you some numerical guarantees. So in a sense, if you can calculate, for example, this active susceptibility up to a certain error, then I can translate that into a rigorous bound on TC as well. So in some sense, you can numerically approximate TC up to arbitrary precision in a rigorous way. It's almost explicit. Yes, sure.
What if half the vertices had maximum to be 3 and half of them had maximum to be 2 or something?
Yes.
Sine went off and then maximum to be 3.
Okay, so our proof. Okay. So the only question for a proof would be if the critical time there happens at the end or before the end, and this. But otherwise, the machinery carries over. I haven't checked actually in this example whether it happens before the end or not. So because in that case you have average degree. No, it's 2.5 average degree, right? No, okay. So there it happens before the end. So yeah, so
It always happens before the end.
No, in this case, because if the average is larger than 2,
Anything else?
So as soon as you go above 2.
Yeah.
Oh.
But if you go up, so this in this sense, this 2 process is a little bit annoying, right? Because it says if you're just too regular, something else happens. If the average is bigger than 2, then our other proof always applies. In the other case, the question is, can you decide whether the critical time is before the end or not? This is a little bit of a delicate issue. Because it could be, in this case, you sort of run out of time, as in the 2 process. Maybe everything only happens on the last few steps. And this is sort of a very special behavior, which is not so easy to characterize in general.
anyone else? All right, let's thank Lutz again. Thank you.
Now that they've been dismissed, I have a couple.
You
So
thought-
you're not
You
dismissed.
thought you were,
Okay, yeah,
you
we
were
can
out,
wait.
but-
So you and Svante were talking about your simulations. And you said they're not simulations, but you put simulation in your table, so there must be more to the discussion as to
Okay.
whether they're simulations or